Hlér will talk about witnessing latent time correlations with a single quantum particle. And I think, yeah, we can start. So please.
Okay, so what's time now? All right, thank you very much for the introduction, and very happy to be at the live conference again. So welcome to my talk on witnessing latent time correlations with a single quantum particle. I'm Hlér Kristjánsson, and this is joint work with Wenxu and Giulio Chiribella. So in this talk, I'm going to talk about communication channels with correlated errors between successive uses of the channel. So let's consider a standard communication scenario between a sender Alice and a receiver Bob through some transmission line. So we can imagine that Alice wants to communicate some information to Bob, and so she will encode her information, her message, in the internal degree of freedom of some particle, for example, in the polarization of a single photon. And then in order to send a message to Bob, she will basically send a succession of particles through this transmission line, which will be noisy in general, and in general will have some correlated noise. So whatever noise occurs on the first particle will also be correlated with the noise that occurs on the second particle, and so on. So in general, Alice will encode a message over a sequence of particles and send it through. Now, if we know the structure of these correlations, we could encode one logical message on a sequence of multiple particles in such a way that allows us to mitigate some of the errors. And classically, the use of multiple physical particles in this case is necessary. But in this talk, I'm going to show you that in quantum physics, in fact, a single quantum particle can probe the correlations between successive uses of the same transmission line and allow us to perform, again, mitigation of the errors using this technique. And we do this by transmitting the particle at a superposition of two different times. So for the introduction, we already had. So the rest of the talk, I'm going to talk about time-correlated channels, so the formalism, then how to transmit the superposition of different times through such channels, and then I'll discuss the communication advantages and finally conclude. So the framework is the following. A transmission line that could be accessed at k different times is described by some k-step quantum channel, which is just a CPTP map which transforms states of the composite system S1, tensor S2, tensor S3, and so on up to Sk, where the system Sj denotes the system sent at the jth time. It just acts on a tensor product of systems at different times. For example, a two-step random unitary channel is given by equation 1, which essentially consists of a system S1 sent at the time T1, and a unitary UM acts on that system. And then at time T2, you send some system S2, so another state S2, and this undergoes some unitary UN, some random unitary UN. But the randomness is correlated between the two uses, so described by this probability distribution PMN. And so the overall state that this channel acts on is the composite state rho 1, 2 over the two times. Now, this is well defined within quantum channel theory. These kinds of situations have been studied quite a lot. But in this, we kind of imagine that we have a particle sent at time T1, S1, and another particle at time T2 through system S2. And now I'm going to describe how we can in fact just send a single particle in a superposition of going through at T1 and T2. The way we do this is the following. So we assume that each system S1, Si, I could be 1, 2, 3 up to K, has a d-dimensional one particle subspace, which corresponds to the message that we're trying to send, and a one-dimensional vacuum subspace. So this could, for example, correspond to single photon polarization. So imagine we're encoding information in the polarization of a single photon. Well, then there'll be a two-dimensional message and a one-dimensional vacuum. The vacuum means that we don't send the particle. So at every time, Ti, if the particle is sent, it affects the internal degree of freedom psi of A is this one particle subspace. If this particle is not sent, it acts on the vacuum state. So if we now send the particle at an equal superposition of the two moments in time, then we get a state of the form below, where we have a linear combination of psi, so the particle sent at t1 and the vacuum at t2, and not sending the particle at time t1, so the vacuum is in time t1, and the particle at time t2. So I hope that all makes sense. So we now consider channels which conserve the number of particles. So if the channel conserves the number of particles, then every unitary that we considered earlier, UM, decomposes in the following way. There is some block VM, which acts on the one particle sector, and another block that's just the identity on the vacuum. But crucially, with some non-trivial phase between the, the one particle and vacuum states. And this is indeed the case for linear optical elements, for example. So, for example, phase shifters would work in this way. Now we consider the case where the time of transmission is controlled by some quantum degree of freedom, by a qubit. For example, it could be the time bin degree of freedom of the same photon that we're using to encode our message. So if it's in a computational basis state 0, then the message is sent at time t1, the vacuum at time t2. If the control is in the computational basis state 1, the vacuum is sent at time t1 and the particle at time t2. And the effective evolution, now, in this case, if the control is in the computational basis state, so in a classical state, is given by equation 3, where we can see there's a trivial sum over the nth index, which means that we are actually independent of the correlations between successive time steps. So this is what you would expect. Classically, if I send a particle at a definite time, then I cannot probe the correlations between successive times. So that's exactly what we would expect. But if the control state is in a quantum superposition state of the classical basis states, 0 and 1, so in a superposition state omega, then the overall evolution of the whole system is now given by equation 4. So we call this effective channel C subscript omega, where omega is the state of the control system. And this depends on both the correlations P m n between successive uses, and it depends on these vacuum phases phi m. So what can we do with this formalism I just described? Well, let's consider an extreme example of a very bad channel, so the completely depolarizing channel, which I denote now C subscript JJ. So remember, J is the computational basis state. So the completely depolarizing channel on a definite time step is described by this effective evolution. So C JJ, so J is any computational basis state, just gives you the maximally mixed state on the message and the same control state in the control. So in this case, clearly no communication is possible at a definite time step. And just to note, this for qubits, which we'll look at later, this can occur when the unitaries UM are the identity and 3 Paulis. So U0 is identity, U1 is X, and so on. But now, if this transmission line in fact has correlations between successive uses, for example, with the probability distribution PMN equals Kronecker delta m comma sigma n, where sigma is some permutation of the unitaries. So it just means that if I have a unitary UM that occurs at time t1, and deterministically I will get another unitary determined by that permutation at time t2. Well, in that case, when the control is in the plus state, I get the equation 6, where we have this interference term G, which, as you can see here, depends on the correlations of vacuum phases. And for the identity permutation, we can see, so identity permutation means that whatever unitary had at time t1 happens also at time t2. Well, then this G thing just is a maximally mixed state, and if you plug that back into equation 6, again, we get a fixed state, so no communication is possible. However, if we have a permutation sigma which permutes I and X and Y and Z, then we get an interesting result, namely that it turns out that for certain choices of vacuum phases, we can get a non-trivial classical capacity. In fact, if you look at the plot we have here, in some cases we can even get perfect classical capacity. So we can get 1 bit per use of the channel. Concretely, if we consider these choice of vacuum phases, which is a non-trivial choice, which you can see here, we get that G acting on the plus minus states has plus minus identity over 2. So in particular, when the controller is in the plus state, if Alice encodes a message in either the plus or the minus states on the internal degree of freedom, then this message is transferred deterministically to the control system after the noisy evolution. So what does this mean? We've taken a transmission line which was completely noisy, completely useless at any given definite time step. And yet we now see just a single particle again. It's still a single particle, but in a superposition of the 2 possible times of use of this channel, and we get a perfect transmission line. Now, just to say, at present we have an experimental collaboration at Imperial College, where we're trying to implement these things in experiment, and in particular looking at these vacuum phases and their structure a bit better. How are we doing for time? Sorry, 14. So before we get ahead of ourselves, let's remind ourselves where these communication advantages are coming from. Well, we can see that in equation 6, the output state here depends both on the correlations, PMN, but it also just depends on the effect of coherently controlling the time of transmission. So we can ask a natural question whether we can get the same communication advantages just by coherently controlling the time of transmission, even if there are no correlations between the 2 uses. And we prove in this work that the answer is negative, namely that whenever the probability distribution factorizes in this way, so we have a completely depolarizing channel at each time step, is independent of the other depolarizing channel at the next time step. So probability distribution factorizes as follows. Then when the effective channel isn't with control state in a plus state, so equal superposition of the times, we then get an output state which we call C subscript plus plus comma F, where F is what we call the vacuum interference operator, which depends on the correlations only at, sorry, the probability distribution only at a single time step and the vacuum phases. And the proposition is the following, that the classical capacity of the channel C omega F for any control state omega is upper bounded by the following equation, inequality 9, which depends on the norm of the operator F, and for qubits reduces to a bound of 0.5 bits. So remember we had 1 bit was the maximum capacity advantage we got, which is actually the maximum capacity you could possibly send. And we managed to achieve that with the correlations. But without correlations, we can only get 0.5, and that's an upper bound. Later, we'll actually show you that this is not tight. So a quick sketch of the proof. So I don't have time to go into the details. So the way we prove this is, if you look at equation 8, so this is the equation for a superposition of times of independent, completely depolarizing channels. Well, first we just prove that this channel is entanglement breaking. And we recall that for entanglement breaking channels, the classical capacity coincides with the Hollover capacity. We then prove that the control state plus maximizes the Hollover capacity of this channel. And then we prove that in the lack of correlations, so in the case that we just considered, the completely depolarizing channel with no correlations, any message that mentioned d greater than 2, then the Hollover capacity is upper bounded by 1 over d. And this has some further sub-steps. So for example, we recall the inequality 10 for a general quantum channel for the Hollover capacity. We then prove that the channel we just discussed, acting on any pure state, decomposes into a sum of projectors, orthogonal projectors, which means we can calculate the von Neumann entropy and therefore the Hall capacity very easily. And then we use the Cauchy-Schwarz inequality to prove that the norm of f is always less than or equal to square root of 1 over d. And just plugging that back into, taking equation 8 and plugging that in gives us the bound that we have here in the proposition. So then we can actually bound it even further. So what we do now is we prove, basically what we did earlier was we proved the analytical bound that cannot possibly be exceeded, but then it's not sure if it's achievable or not. So we'd like to do a numerical simulation to check actually the classical capacity. But of course, in general, to calculate the classical capacity is very complicated. To check over all states, you might need a supercomputer, or I don't know if it's even possible. So we prove a theorem that says, for this channel, the completely depolarizing channel in a superposition of 2 times, independent with no correlations, that channel is upper bounded by some quantity here, maximized over 3 states. So 2 real pure states and another state that is sort of formed by from those 2 states with some projectors. And this allowed us to just plug in those states, and we check over all possible states of this form, which I could just do on my laptop, which is quite old, and you can do that very easily just in a few minutes. And you get the exact classical capacity up to whatever numerical precision I chose on my laptop, given by this 3D graph. So you can see for different vacuum phases, I get a different Hall capacity, which, as we said before, in this case is equal to the classical capacity. And we find that, in fact, the highest thing you can get is 0.16, which is almost an order of magnitude smaller than the maximal 1 bit we got at the beginning with the correlations. Now, unfortunately, in the interest of time, and this proof is beyond the scope of today's talk, but it essentially relies on a combination of linear algebra and group theoretic techniques. So if you're interested, please check out our paper. But that is it. To summarize, what we've seen is that a single quantum particle can sense the correlations between noisy processes at different moments of time. And the particles sent at a superposition of different times can boost the communication rate of noisy channels to values that would have been impossible if the moment of transmission were classical. And yeah, I should probably just say as well that we also studied the robustness of this protocol to noise on the time degree of freedom. So if the 2 different times are decohered a little bit, then this protocol can still give us advantages, essentially up to the amount of decoherence that we had. And if you're interested in this framework, then please look out for our upcoming paper about quantum networks with coherent routing of information through multiple nodes, which extends this framework of coherently controlling a single particle from just individual channels to entire communication networks. So with that, I would like to thank you for your attention.
All right, thanks for a nice talk. You're interested in these upper bounds, right? And so there are some known upper bounds from Xin Wang et al. And Fang and Fawzi. They're like semi-definite programming upper bounds. They applied to generic channels.
Right.
I'm just curious if you looked at those and if those are relevant for the scenario you're looking at.
I'm not familiar, unfortunately, with those bounds, but are they about general channels or superpositions of channels?
They're for general channels,
right?
But, I think your channel is a general channel, right?
Yeah.
So
yeah, that's interesting. I'll take a look at that in the future. Yeah, I can't comment on that right now.
Sure.
But thanks for the comment.
Yeah.
Hi. So it's an interesting talk. So I see one of your slides shows that you can use you can send a photonic state and based on the control of your qubit 0 and 1. And is it also possible that send any qubit in Hilbert space through this time being coded photons?
That's a very good question. So essentially, this scheme relies on the fact that your channels decompose in this block diagonal way. And that comes naturally when you have single photons, because you always have this one-dimensional vacuum that is basically is unaffected by application of the devices. So in any other scenario you might be interested in, and that's not always the case, but if your channels are block diagonal in this way, then you can construct this protocol. But if not, then it wouldn't be possible.
So you do consider the qubit, right?
So the message is a qubit, but the total Hilbert space is a qubit plus the vacuum state. So it's essentially a Q-trit. So this is actually a slightly complicated the mathematical formalism which I skipped over. But essentially, what happens is that you have two. So you've got imagine an interferometer. So you have a single particle in a superposition of going to the left and the right-hand arm of an interferometer. Well, then, if you encode your information on the message or polarization of the particle, then you would really have a horizontal and vertical polarization and vacuum on each arm. So that's 3. That's the Q-trit and the Q-trit. But because you only had one particle, then the total Hilbert space is actually not 3 times 3 dimensional. There's correlations in the Hilbert spaces. So you could only have, if you have a particle on this arm, then you have a vacuum on the other arm, and vice versa. So the total dimension of the Hilbert space is actually 4.
Okay.
In fact, this is something it was in, well, poster session is over now, but we discussed that in the poster session. But thanks for the question.
Thanks for the talk. So could I just ask about these phases with the vacuum? These are something that you can really control and measure. Isn't there kind of a fundamental difficulty here with these, even defining these phases and having them stable in time?
Yeah, so good question. So I suppose there are 2 points of view here. So if you have a device, just a transmission line from Alice to Bob, then that transmission line is a quantum channel described by a quantum channel, and the quantum channel acts on the Hilbert space or the internal degree of freedom of the particle and the vacuum and all combinations of diagonal elements. And so that channel will, by definition, have a fixed phase, because I mean the device will have a fixed phase phi. So I suppose perhaps if you're thinking about correlated channels, that phase might change in the 2 applications. But so far we assume that this is just part of the specification of the communication device and that this doesn't change. And I mean, if you look at the optical, like if you go to the lab and you see some optical elements, then they will have a fixed phase that just depends on how they're manufactured. So in the communication, because these are noisy channels, we assume that the phases are fixed. But of course, if you wanted to just make a proof of principle experiment in quantum optics, then our collaborators at the Imperial College, for example, they're trying to scan or understand these different phases. Then you would just put the phase shift on one of the arms of the interferometer, which reproduces the action of having a variable phase between the vacuum and one particle.
Sorry, what's the interferometer here?
So, So we were talking about, in this talk, I was talking about sending a single particle a superposition of different times. So a more simple thing that is actually described in exactly the same way mathematically is a superposition of paths. So you have one channel on one arm of the interferometer and the other channel on the other arm. And then you could just put the phase on the one of the arms. In time, it's actually more complicated, so we're still working on how that would work.
Okay, thank you.
Thanks.
Thanks for the talk. So I'm not sure I understood completely, but it seems to me that essentially you gain more information the more the 2 uses of the channel are correlated, right? So in principle, you can imagine a limit in which the 2 times are really, really close.
Right. So, okay. So it's not quite that simple. The thing is that, so maybe the most easily imaginable correlations in an experiment would be the correlations, let's say in a photonic setting, would be from birefringence. So if the channel has some noise comes from birefringence, and then the time scale of the birefringence changes changes slower than the time at which you send two particles, then indeed what you said would be correct. But because we showed earlier that in fact the identity permutation, so if actually the noise doesn't change between the two uses, that's actually useless. That's not helpful. We need some strange types of correlations. So these strange types of correlations, I mean, the exact physical scenarios that they would occur is something we haven't maybe completely figured out yet, but it's sort of a proof of principle, just that there exists types of correlations which may or may not exist in certain scenarios that can give us these communication advantages.
So it's not enough, say, the same noise, but with a different phase.
Exactly, no, that's not quite it. It needs to be that, for example, one of the cases which we discussed is where really if I pick identity unitary in the first time step and I get the X unitary in the second time step, it has to be this kind of deterministic correlation between the choice of unitaries.
Okay.
Yeah.
Thanks.
Okay, thank you.
Yeah, perfect. I think time is up for now, but of course we can continue the discussion. Let's just thank all the speakers of the session again.
Thank you.
I think the next event is at the Hilton Pasadena.